Good morning, General, Mr. President, hero of the people, great helmsman, eternal president, Emperor. Going the Bokassa route. Nice. I, like many others, have noticed that your country is being dragged in the mud over the Civil War. That rebellion you won. The rebellion you crushed. You defeated those dastardly invaders. Overthrew the oppressors. You won that election. You get the picture. What I'm offering you and your country is a chance to improve its image. Food and literacy programs? Nah, those are basic and uninteresting. You need something big, bold, and contentious. Orbital launch capacity. And not just any old rocket. We're talking about an ultra-modular pressure-fed launch vehicle. We're gonna go old school with this. OTRAG.
¿Este es el gringo de los misiles?
Morning, everyone. I designed a better OTRAG. Now, when I say I designed a better OTRAG, I don't mean that this is going to turn into an investor's pitch. So if I see a Better OTRAG Incorporated show up on my social media feed soon, I'll know it was you, and I'll be calling my lawyer. That's right, I'm back. The analysis here is more of a parametric study, which I'll get into the details of soon. And I'm going to warn you right now, you're going to hate math by the end of this. But we'll end up with a better OTRAG. It's not that. All right, so here's what we're going to cover. I'll talk about the history of OTRAG, how I'm going to improve the design, the methods I'm going to be using, 4 rounds of studies, the better OTRAG, its performance, and the launch vehicle family it'll create, and then we'll discuss the practicality and alternatives to the design. You can see that here, and you can see the chapters on the bar, or you can look in the description. Also in the description, I have 3 things. A paper version of this study, a spreadsheet covering the design details for the better OTRAG, kind of how I arrived at the design, and then the third one will be a way of seeing what the OTRAG family can do and what the alternatives are. So if you want to read the study beforehand, feel free. If you want to follow along, feel free. That's up to you. And yes, this is going to be one of the long ones. Ready?
I'm replacing Parliament with a junta in 45 minutes, so be quick.
To start, some history. Orbital Transport und Raketen Aktiengesellschaft, OTRAG, is the first privately funded rocket company, founded in 1975 by West German engineer Lutz Kaiser. Originally a Europa 3 contender, the launch vehicle followed the minimum cost design approach, or as it is better known, Big Dumb Booster. Big Dumb Booster is the alternative to reuse when it comes to low-cost launch vehicle design. Reuse says that you should somehow bring back expensive rocket hardware and use it again, while Big Dumb Booster says, stop throwing expensive things in the ocean. OTRAG does Big Dumb Booster with a twist. Almost all launch vehicles, like this one, have dedicated stages to them. Big Dumb Booster included. In this case, the TRW low-cost launch vehicle, the stages are designed to be geometrically similar, but they are dedicated and different stages. OTRAG doesn't do that. Instead, it's made up of small rocket propulsion units that are strapped together. It is designed around mass production, like most common consumer goods these days, which could drastically reduce costs. And of course, it's also a pressure-fed, which... The propellant would be a 50-50 mix of nitric acid and dinitrogen tetroxide, also known as high-density acid. Diesel oil would be the fuel. The propellants have the benefit of being very dense, cheap, and an acceptable performance. Tank pressurization, because this is pressure-fed, would be as simple as can be. Blowdown. The tanks would be filled with compressed air at 580 psi, and once the valves opened and the fuel started draining out, the pressure would drop accordingly. Each unit would have two moving parts, the oxidizer valve and the fuel valve. And that's it. It's very simple. OTRAG's design has three key factors over other launchers. The first and most important one is scalability. You can bundle rocket propulsion units together to make a wide variety of launch vehicles. OTRAG itself sold a launch vehicle as small as 200 kilograms to low Earth orbit and one as big as 10,000. The second one, which is also related to scalability, is optimization. Because you're clustering small rockets together to build big ones, you can optimize your rocket to meet different mission requirements. 3, 4, 5, maybe even 6 stages in one rocket. You really can't get that with other launchers. Thirdly, the ultra-modular approach means that you could theoretically have a faster development cycle since you can crank out units to test and iterate on. OTRAGs will be made of two possible units. Now, both of these units will be constructed of 3-meter high and 27-centimeter diameter segments that will be stacked on top of each other using bayonet attachments. The first possible unit type is the single unit, which has both fuel and oxidizer in it. And the first possible configuration is that it's classic. We got oxidizer on top, fuel on bottom, but I couldn't find any diagrams with fuel lines inside or outside the unit. So the second possibility is more likely, that the tanks were concentric. Also, the last 3-meter segments that were flown in S range in Sweden had concentric tanks. A 24-meter tall unit would contain 1,350 kilograms of propellant and weigh 1,500 kilograms full. The engines would start at 35 kilonewtons of thrust and then drop to 15 kilonewtons by the end. The second type was a quad, where 4 tanks are clustered together. 2 would be for oxidizer and 2 would be for fuel. The fuel tanks, since they had less fuel in them, would also contain most of the compressed air for the unit. And if you want to do the math for that, just multiply everything by 4. The engines were designed to have specific impulse of 245 seconds at sea level and 295 seconds in vacuum. OTRAG suffered 2 major technical issues, aside from the ones we're going to talk about at the very end. Those engines got the right thrust, but not the right specific impulse. Instead of 245 seconds, try 185 seconds at sea level, and 235 in vacuum. Now, Kaiser did claim that the clustering of the engines would make them form a jet that would increase specific impulse by 6 to 10%, but in reality that's negligible to 1%. The units were supposed to be lighter than what was stated. The 24-meter units were supposed to have a mass ratio of about 10, where the dry mass is about 10% the weight of the total vehicle. In reality, it ended up being somewhere around 15%, which isn't unreasonable for Big Dumb Booster, but awful for OTRAG. Combine that with the poor engine performance, an OTRAG launch vehicle either couldn't make it to orbit, or the payload capacity was so limited that it destroyed all the cost effectiveness. What? Me? Oh, I'm on vacation in this very tropical location that's gloomy and looks like it's gonna rain. There was a political element to OTRAG's failure too. Okay, I'm listening in on you. Okay, you got me. You're a guy proposing an ultra-low-cost launch vehicle in a nation that's not the United States. We're concerned. OTRAG obviously couldn't do tests or flight tests in West Germany because they'd land on people's houses, or worse, the other side of the Iron Curtain. Instead, they went to Zaire. France and the Soviet Union combined to make propaganda about OTRAG to get them kicked out of Zaire. And just for reference, Zaire was a dictatorship at the time. If you're going to go build your rocket in a country that's not the United States, you're going to run into some issues, politically and legally. For example, if the country you're going to is prone to near constant civil war, conflict, to the point where, let's say, an eastern half of your country has rebel groups still from a conflict from 20 years ago, that's going to be an issue. Or if your country was once run by the quintessential African dictator, that might be an issue for you. For example, I'm talking about the Democratic Republic of the Congo, also known as Zaire. They then ended up in Libya and did a few more flight tests there until the Libyan army seized the site and their equipment. At around the same time, Germany became party to the Missile Technology Control Regime, which is an agreement for countries like Germany, the United States, who have missile technology to not share it with other countries like Libya. Or another issue would be if you go to a country that really, really wants orbital launch capacity, especially with a launch vehicle like yours, that will eventually, I don't know, seize your rocket company, its assets, and then use that to build low-cost missiles. Also, if this flamboyant dictator of yours is notoriously antagonistic to the United States and its allies and does, I don't know, state-sponsored terrorism against them. You know, like Libya under Gaddafi. Don't build rockets in third world dictatorships. The political blows, combined with the fact that everyone was realizing that OTRAG wouldn't work as an orbital launcher, caused the company to fold in about 1985. OTRAG hasn't faded out of existence, however. There have been successors to the design. No, modular systems like Percheron, Conestoga, or Scorpius don't count. OTRAG is ultra-modular. In the early 2000s, both Armadillo Aerospace and Interorbital Systems approached Lutz Kaiser about building an OTRAG-style ultra-modular system. Armadillo was planning to build a hydrogen peroxide kerosene system that closely resembled OTRAG that I can't find anything on, except that Lutz Kaiser gave them an OTRAG injector head. Interorbital has sought to build their own version of OTRAG, and they've fixed a few of the issues with it, such as turning the quad unit into the basic unit with one engine and using composites. They've also switched to using white fuming nitric acid and turpentine for fuel. Now, they've built one or two test articles and did one test launch that I know of, and haven't done much since 2017 except announce an entirely new rocket. I don't think they're too serious. Another design I've seen is the unreasonable rocket. Now, this would be an ultramodular approach using peroxide and an unknown fuel that used to be gasoline to build a either suborbital rocket or a small orbital rocket. Now, this one's an amateur effort, but good on him for thinking about that. Then there's ARCA announcing this atrocity. I can't even remember its name. I just call it, oh no, TRAG. It's steam-powered and partially reusable. They're not serious. So you're going to notice that OTRAG isn't too popular of a design. Some of you will even say, well, there's a reason for that, in that funny voice I just made. But you have to remember that aerospace, especially the space side of things, is a very conservative industry. They're more of a follow-the-leader type industry than anything else. Take a look at the recent batch of small-sat launchers and tell me if you see a pattern. If you look at the history of private launch vehicle development, you will find plenty of workable and feasible ideas that didn't go anywhere because they just ran out of funding. Funding! I completely forgot. I've got my lawyer, I got guns, but I forgot my funding guy. I'm gonna call him right now and make sure he made it through customs. Yeah, well, okay, I have a plan. It's a great one. It's called cryptocurrency. Here's what we're gonna do. We're gonna make a coin, OTRAG coin, Kaiser coin, modular coin, whatever it's gonna be. We're gonna get YouTube stars, Instagram influencers, anyone we can think of. And we're gonna get a bunch of people to put a lot of money into it. And then, when we reach a certain amount, we take it. Quick question. Does the country we're going to have any extradition treaties with the United States, Europe, NATO, the EU, OPEC? Hello? I need new friends. Here are the improvements I'm going to make for Better OTRAG. 1. The quad unit from the old design is going to be the basis for the new one. The small ones were just too small. Now, I am going to sacrifice some of the ultra-modularity, but I also need a rocket that actually works. So this will take the 256 unit down to 64. 2. I'll be making 3 engines instead of 1 and optimizing them for the different stages. Yes, this will again cut down on the ultra-modularity, but I still need an OTRAG rocket that can carry useful payloads into orbit. Tank pressurization will also be done using a regulated gas feed system instead of blowdown. It's more complicated, but it keeps engine performance consistent. 3. This study is going to examine alternate materials and propellants for the Better OTRAG. A vague reference to a 250,000 psi tensile strength steel is not going to cut it. Also, NTO, dinitrogen tetroxide, is now $6 per kilogram and is incredibly toxic, which does not make it attractive as an oxidizer today. 4. The unit size is probably going to change. OLDTRAG was optimized around 24-meter tall units that were 27 centimeters wide. I'll be starting with a 24-meter high unit that is 27.94 centimeters across, because, okay, 11 inches is a much easier round number to work with than 10.65. And if needed, I will optimize the unit sizes. I'm not just going to make a random design and say, mission accomplished, and then be done with the whole thing. I actually have to meet some requirements. Since the 256 unit OTRAG is the baseline I'm going to go for, it has to carry 4 metric tons to LEO at 70% capacity, which means at full, 5.7 metric tons. Now, since the quad unit is now the single unit, that reduces the number of units from 256 to 64. 4 on the third stage, 12 on the second, and 48 on the first. The payload mass must be greater than 1% the gross liftoff weight. This follows the trend set by OLDTRAG and is true for existing launch systems. It doesn't matter how cheap your rocket is, but a 1,000-ton CubeSat launcher will never be practical or efficient as a design. Pricing will play a role in the design of Better OTRAG. The 4-ton baseline should get about $9,500 per kilogram at the worst case scenario, which is where propellant is about 0.5% the total launch price. Now you think that might be high and really unreasonable, but it actually fits the pricing of similar launch vehicles of that size and capacity. And ideally, when propellant is 2% the price of a launch, OTRAG should be about $2,500 per kilogram to meet what Lutz Kaiser said it could do. I will note that my pricing scheme is crude and rudimentary. It obviously favors low weight and high performance systems over others. In reality, of course, a high performance engine like a turbopump fed system is most likely going to be much more expensive than a simple pressure fed that has lower performance. Now let's get to the methods. Math? Methods. The big obvious one here that we're going to start with is the fact that Better OTRAG has to have a delta V of 9.5 kilometers a second. Now, that might seem high to you, considering I've used 9.3 before, but you also have to remember, does this thing look aerodynamic to you? And I'm also going to try to build in conservatism to the design, and this is one of the obvious places to do it. The payload fairing is going to have these dimensions. So it's going to be as wide as the vehicle, which should be obvious. The cubic section is going to be 3/4 that width in height, and then the pyramidal section is going to be half the width in height. I picked this because it's aesthetically pleasing, and once I get farther down, I'll start optimizing the height. To calculate the payload fairing mass, I'm going to use the surface area to the 1.15 power times 4.95, and then I'll be adding a conservatism factor of about 20%. And this mass will be added to the first stage of the Better OTRAG. On the third stage, I'm going to include the calculation for the mass of the payload attach fitting, because that's not included in the basic unit mass calculations. And I struggled to find a calculation for this. The only one I found is this, where the mass of the payload attach fitting is 0.755 times the mass of the payload plus 50. Now, when I started doing the math on this, this ended up being rather heavy. So I'm just going to say this is also the guidance and navigation system. This will be, everything else that gets involved with the third stage that can't be part of the structural mass of a unit. I will also be examining three possible unit types for the Better OTRAG. Quad, concentric, and inline. Quad is, of course, based off the old OTRAG design. Concentric is also sort of with the last units, and then inline will follow the design style of every other launch vehicle. Quads are, well, quads. 2 oxidizer tanks, 2 fuel tanks, and 2 pressure tanks on top of those. These are favored structurally because they give you that classic OTRAG look. The downside is that you have double the part count because 2 sets of tanks compared to the other 2. And you're also stuck exclusively building rectangular prisms out of these. Concentric tanks are a similar alternative. Your propellants will be operating at the same temperatures and pressures, so you can put them next to each other in a tank. The real benefit to this one is it's a single cylindrical unit, which means you can build other shapes, like hexagons. The downside is, how do you assemble this by putting the concentric tank in the big one? Remember, these are tall and thin. And the other one that's more of a middle ground issue, if you ask me, is if you have hypergolic propellants and there's a leak, you'll know very quickly. And then there's inline, which is oxidizer tank on top of fuel tank with a pressure tank on top of the oxidizer tank. This one was rejected for 2 big reasons. The first and easiest one is that the oxidizer tank will have to operate at a higher pressure than the fuel tank, which destroys ultramodularity and how I want to build this thing. Secondly, I'd have to put a feed line somewhere between the oxidizer tank and the engine. And you can't put it on the outside because it's modular. And if you put one on the inside, well, you've just made a concentric tank. Remember, tall and thin. Now they have possible units, I'm going to do the tough part, structural analysis. Now, I'm not just going to guess what that is based off what other launch vehicles have. I'm going to do some math. This is our basic OTRAG tank unit and the forces that are acting on it. I'm excluding bending moments. So you got aerodynamic forces coming in axially, same with thrust, squishing it. But you also have internal pressure that's going to go into tension. And then on the hoop side, because this is a cylinder, you have atmospheric pressure wanting to squeeze it, and then you have internal tank pressure pushing outward. Atmospheric pressure in this case will just be neglected. So how am I going to work with all of these in tank design? I'm going to assume stress from internal tank pressure is going to be greater than all of those. On conventional launch vehicles, this would obviously be a dumb decision. But you have to remember, this is a pressure-fed launch vehicle. The propellant tanks have to operate at a higher pressure than the combustion chamber. To give you a sense of this, the Space Shuttle external tank operated at about 35 psi. Mine, 350. These are the equations for axial and hoop stress on the tank. Sigma here is not referring to just you, the viewer, but the stress. So if you work these equations around to calculate the thickness that you're looking for, you're going to discover that axial thickness will be half that of what you'll get for hoop. So I'll be using hoop thickness for my calculations. And in this instance, sigma will be the maximum allowable stress from the material we'll be using. Here's a screenshot of material data from MATLAB. Now don't panic, we'll be looking at 2 specific numbers, yield stress and ultimate stress. Metals, like the ones we'll be looking at, have both of these. Some materials don't. Yield stress is the point at which a metal, if undergone enough stress, will stop bouncing back to the original shape and deform before breaking at ultimate stress. For example, this half of a dog bone segment made of steel, you can see it was necking and then broke at ultimate. It's a lot like rubber bands, right? You keep pulling on them, they bounce back until at some point they stop, thin out, and break. For this study, I'll be using yield stress with a safety factor of 1.5. Now, for a quick refresher on why we're using safety factors, your launch vehicle is going to undergo, or at least your tanks will undergo, a range of loads. Best case, worst case. And your material is going to have a range of yield stresses that it's capable of supporting, because not all materials are identical. So a safety factor is a way of making sure there's a safety cushion between the maximum loads and the worst case scenario for your material. Then for the metals, I'll also be adding another factor of weld efficiency, because I'm assuming I'm going to be welding this thing together, of 85%, further lessening the strength of the material. For fibers, of course, there's no weld efficiency because you're not welding them. This means that tank wall thickness can be calculated as pressure times radius over maximum allowable stress. Now you notice that pressure is broken up into two parts: ullage pressure and hydrostatic pressure. Ullage pressure is 1.26 times the chamber pressure, because this is a pressure-fed system. Then the hydrostatic pressure is because, well, if you think about it this way, when your rocket's taken off, it's going to have fluid in it, and the fluid is going to want to get out the side. So you need hydrostatic pressure. That's calculated by acceleration times height times density. Acceleration in this case, I just said, was 3 Gs, because anything else would require analysis that I wasn't willing to do. They got the height, which is the height of the tank, and then D is the density of the oxidizer. I'm going to set the fuel tank wall thickness to be the same as the oxidizer tank thickness for practical purposes. You don't want to end up having to buy multiple grades of steel for your rocket. Now, end caps are a bit trickier to do. In this case, I picked my end caps to be half the height of the radius. And then you have to do these icky equations. But luckily, for this case, and pretty much this case only, the thickness is the same as doing cylindrical sections, only without the hydrostatic pressure. Pressure times radius over allowable stress. I can then use the thicknesses I got to calculate the tank weights, masses. It's in the paper. Okay. Cylindrical is pretty easy. End caps are a bit more challenging, but I can use these to calculate tank weights and then get dry unit mass. And one more thing, the tanks are not 100% filled with propellant. I'm leaving 3% of the volume available for ullage, because you need to get the gases in there somehow. It's easy for propellant management. And for the oxidizers, I'm going to reserve 1% of the oxidizer mass for liquid injection thrust vector control, start-stop procedures, just for spare. In the case of the pressure-end tanks, on the quad unit, it'll be based off of the remaining volume available on the quad. And then for the concentric tank, it'll be based off of the assigned value. For calculating the tank pressure, I'm just going to assume that there's adiabatic expansion going on, and I'm going to avoid all the fun thermodynamics. This is the equation I used to calculate pressure-end tank pressure. Pressure-end tank pressure equals the pressure of the propellant tanks times this factor, which is the volume of the propellant tanks, total volume, divided by the useful pressure-end tank volume to the power of gamma plus 1. Now, so, okay, propellant tank volume, that's obvious, but useful pressure-end tank volume is, like with the propellant tanks, I'm going to assume that a percentage of it is not used, so that's 5% of it's just going to be hanging around, loitering, whatever. And then in this case, gamma is 1.4, since that's the ratio of specific heats for nitrogen, which is the pressure I'll be using. With the tank masses calculated from the methods I used before, I can estimate the total dry mass of a unit. Conventional big dumb boosters sit at around 62%, but OTRAG isn't like a conventional BDB. Instead, I'm going to assume that tanks are 50% the weight of a unit. But I will add a 10% conservatism factor, just for good measure. A factor I like to use in my analysis is what I call the structure ratio, the ratio of dry mass to the propellant mass in a unit. For classic BDBs, it's somewhere around 12%. What it ends up as depends on a few factors. All I know is that it can't be less than 6%, so any number less than that will be rounded up. Now, let's take a look at our materials. Okay, I'm going to do the list here. Maraging 250, a classic high tensile strength steel considered in the original Big Dumb Booster studies. What now? Maraging steel has high tensile strength, but it also has high ductility, which means it can take a lot of loading cyclically. In places like, oh, I don't know, a uranium enrichment centrifuge. Just saying. Oh, crap. I've been spotted. Wonderful information. 304 full hard, a strong conventional steel that Copenhagen Suborbitals is using for their amateur space shot. 410 stainless, another strong steel. I hear it's used in car exhausts. D6AC, high tensile steel used in solid motors, notably the Space Shuttle SRBs. 4340 steel, another steel I know that has aerospace applications. 6061 T6 aluminum, the most common aluminum grade available. AirMet 100, a low-cost alternative to more aging steels, because more aging steels are actually quite expensive. S2 glass, also known as fiberglass, a common filament used in pressure vessel construction. Toray T1000G, a high-strength filament used in pressure vessel construction. Material selection for the Better OTRAG unit is primarily focused on getting low weights. However, if it comes to a tie between one or two different materials, I will focus on the more common one. So here's an example. Here are fiberglass tanks rated for 150 psi in my childhood home. Propulsion here is pretty straightforward. I'm going to design 3 engines capable of pushing Better OTRAG into LEO. For propulsion analysis, I'll be using a lot of Hutzel and Hang, I hope I pronounced that, methods. My engines are going to be 15-degree half-angle cones. I'm only going to examine the nozzle, not the combustion chamber. That's just too hard. I didn't have the time to do this. I will be examining 3 combustion chamber pressures for these units, 200, 250, and 300 psi, which coincides with old big dumb booster studies. Now there's 1 or 2 that go above, but I'll be using these. To get the area of the throat, I'm going to use this equation with data from CPropEP. Area of the throat is thrust divided by the thrust coefficient times the chamber pressure. The thrust of each unit is determined by the gross liftoff weight of each stage, divided by the number of units, then multiplied by the thrust to weight ratio. For a Better OTRAG, the thrust weight ratios are 1.5, 1, and 0.5 for stages 1, 2, and 3, respectively. The thrust coefficient is gotten from CPropEP. A quick note on that. CPropEP is a propellant analysis software from about 2000 to 2002-ish. I am aware of CEA, but CEA gave different numbers than CPropEP, and CPropEP has more propellants, and it gives more conservative numbers, so I ended up using that. I included a how-to guide in the study on how to use it, and then I'll also include that in the how-to guide for the spreadsheets as well, just for reference. Now for thrust coefficient, the number you get from CPropEP is the vacuum version. But in reality, your engine's going to have knockdown for efficiency, and for the first stage engine, you have to include the fact that you're going to be operating at sea level first, then going to vacuum. To correct for this, we end up using this equation just for sea level. The thrust coefficient at sea level is 98%, because I'm assuming 98% efficiency, just the knockdown factor, multiplied by the thrust coefficient in vacuum minus atmospheric pressure times area ratio divided by the chamber pressure. That's how you get that. Then for vacuum, we just get rid of this factor and it's just the vacuum thrust coefficient times the 98% knockdown. And voila! You can now calculate the exit radius of the engine and hope it's within the parameters I've set. Not just that, the exit radius of the engines has to be 1.5 inches less than the unit radius. I did this because, well, our engine's going to have some thickness to it, and I'm going to need some space between the engines so they don't bump into each other or interfere with the plumbing. I estimate that the engines will be about 1 inch thick because I measured the thickness of the largest pressure-fed engine ever fired with my pinky. Very scientific. To help visualize the scale of things, this is the width of a unit, 22 inches or 55.88 centimeters, and this is the maximum width of an engine at 19 inches or 48.26 centimeters. And fun fact, this lampshade is about the maximum width. Now, I don't think this has the right area ratio or the right angle, but I think this is a neat representation of the scale of what we're talking about. And then there's specific impulse. CPropEP gives you the ideal vacuum-specific impulse of the engine, but you're going to have some inefficiencies baked in there. For example, the 15-degree half-angle cone will have an inefficiency because since it's a cone, you're going to lose gas out sideways, not going straight down, whereas Bell engines would. So that already lowers it to 98.29%. And then for vacuum engines, I'm going to make it also just 97.5% on top of that. For sea level, since the engine will be operating at sea level through the atmosphere to vacuum, I'll put that at 92%. I have 2 oxidizers and 23 possible fuels for the propellants. Oh, and just in case we weren't clear, this is a liquid biprop. The 2 oxidizers are white fuming nitric acid and 90% hydrogen peroxide. No other oxidizers were considered. Liquid oxygen would obviously boil in these tanks, and unlike conventional rockets, this would be a nightmare to manage. Nitrous oxide has a similar problem where, yes, it is storable at high pressure at room temperature, but it's also prone to rapid phase change. And there aren't any other oxidizers that aren't toxic or horribly expensive. For fuels, I only considered those that were in C-propep, relatively common, were liquids at room temperature and pressure, and did not seem like too bad of environmental hazards. And here they are. Acetyl tributyl citrate. That one's used in making plastics. Castor oil. Vegetable oil made from castor beans. DETA, D-E-T-A, a chemical with historical use in the Jupiter Sea launch vehicle and Scud missiles. Diesel oil, a common hydrocarbon. Also, the fuel of the original OTRAG. Dimethylacetamide, a solvent used in manufacturing of adhesives and pharmaceuticals. Ethanol, alcohol. It was used in early rocketry. Ethanolamine, used in industrial application, and it's slightly hypergolic with hydrogen peroxide. Hexane, a common hydrocarbon used in gasoline. Isooctane, a common hydrocarbon that's the basis for the octane rating system. Isopropanol, a common hydrocarbon used in cleaning supplies. Jet fuel. Now, that's not in C-propep, so I used JP4 as a surrogate for it. It's also the fuel of choice for some low-cost launch vehicle designs. Methanol, wood alcohol. Methyl acrylate, a solvent used in the production of synthetic fibers. 1-pentanol, an industrial chemical. N-butyl acrylate, a precursor to polybutyl acrylate, which is used in items like paint and caulk. Oleic acid, it's a fatty acid that's the most common one in vegetable oils. RP1, gee, I wonder why I picked that. Triethyl citrate, a common food additive that's also used in plasticization of PVC and vape juice. Triethylamine, it's a historic hypergolic propellant. Turpentine, it's distilled pine tree resin that was used in early French rocketry. It's also sluggishly hypergolic with nitric acid. 2,3-butane-diol, an industrial hydrocarbon that's so expensive I've already eliminated it from the study. Again, this is a quick rush through the methods I'm going to use. If you want to get them in full, read the study. And for fun, guess which propellant I end up using? Before beginning, I'd like to walk you through an example for each unit. Now, since this is OTRAG, we'll be going through a 300 psi WFNA diesel oil unit that is 11 inches in radius and 24 meters tall. And yes, I'm sorry for using mixed units like this. The slides here I'm putting up should have both English and SI, or ones I made up, I guess. These units will be made of Maraging 250 for both the pressurant and propellant tanks. Starting with the quad. Since our unit is operating at 300 psi for the chamber pressure, the tanks are at 378. The unit diameter is 11 inches, which means the radius is 5.5, and the height of our cylindrical section is 939.38 inches, because you're going to lose 5.5 from the end caps. Now, nitric acid is 0.0547 pounds per cubic inch. So we add that all together, right? Ullage pressure plus hydrostatic pressure times the radius divided by the weld efficiency times the safety factor Maraging 250 strength, and you end up with tanks that are 0.02 inches thick. That's a little more than half a millimeter, which, incidentally, is the thickness that Lutz Kaiser said OTRAG was striving for. So, for reference, a pop can is about 1 millimeter thick. I can't find a concrete number for it, though, for some reason. What this means is that these tanks are balloons, like on the old Atlas. We'll discuss the implications of this later, but not the question of if you can turn them into animals. Now this means that the cylindrical section weighs 187.4 pounds. Now the end caps, since they don't have this part, are about 0.0163 inches thick, and they will weigh about 0.62 pounds. It's a little over half a pound. Volumetrically, this means that our oxidizer tank holds 4,751.77 pounds of nitric acid. Now remember, 1% of that is reserved for LITVC and ignition purposes, which leaves 1,176.06 pounds of diesel oil. If we do the same math for the fuel tank, it's 399.68 inches tall and weighs 80.18 pounds. On the quad units, this means there's 539.82 inches left for a pressurant tank. Work out the volume, it's somewhere around 48,571 cubic inches. We put this into this equation. Tank pressure that it's going into, the volume of both propellant tanks to the 1.4, ends up with a pressure to tank pressure of 1,843 psi, well within our limits. And the tank wall thickness is 0.0696 inches. Adding up the weights, doubling them, dividing by 0.5, and multiplying by 1.1 leaves the dry mass of the unit to be 2,586.55 pounds. Since the unit carries 11,855.7 pounds of propellant, this leaves the structure ratio to be 0.24. What this means is that this unit is very, very, very heavy, especially compared to the original OTRAG. On to propulsion. Now, for this part, we're only going to examine the first stage engine radii. Now, we already know the weight of a unit, so we can multiply that by 64 to get the overall unit mass, plus a 700 kilogram payload fairing and a 5,700 kilogram payload. This means our OTRAG vehicle is somewhere around 433 metric tons at liftoff. There are 48 units on the first stage, and the thrust-weight ratio for the first stage engines is 1.5, which means that our engines have to have a thrust of 132.76 kilonewtons, or just a scooch less than 30,000 pounds thrust. For first stage engines, I set the area ratios to be 3, 3.5, and 4 for the 200, 250, and 300 psi units, respectively. I did this because optimizing would be way too hard at this point, and because I'm just lazy. So for this unit, since the chamber pressure is 300 psi, the area ratio is 4. Now with CPropEP data, we can calculate the thrust coefficient at sea level, which is 0.98 times 1.43446 minus 4 times 14.7 psi atmospheric pressure divided by the chamber pressure, which ends up being 1.2137. To get the area of the throat, we divide the thrust, which is 29,843 pounds of force, divide that by the thrust coefficient times the chamber pressure. We end up with 81.961 square inches. Exit area is 4 times that, 327.845 inches squared. This leads us to a radius of 10.215 inches. Now, that is less than 11 inches, but it's greater than 9.5, so this would fail. For the concentric unit, I can set the pressurant tank height to be a percentage of the total height of the unit. I worked with 10 to 25%. So on a 24 meter unit, that is 2.4 to 6 meters in total. Knowing this, I calculate the volume of the propellant tank and use the bulk density of the propellant to calculate propellant mass. Since the concentric tank has basically the same math, I'm not going to hold your hand and walk you through all of it. For this one, we're assuming it's 75% filled with propellant or a 25% pressurant tank. So the pressurant tank is 6 meters tall, propellant tank is 18 meters. So you do the math, cylindrical tank thickness is 0.0372 inches. It's a little around half a millimeter. Again, it's more than the quad unit because it's got a greater radius, but not double because it's also shorter. This means the tanks weigh about 518.285 pounds. They carry, in total, 9,635.41 pounds of WFNA and, proportionally, 2,408.86 pounds mass of diesel oil. Now, you do the volumetric calculations, assuming just a cylinder. The radius of the concentric tank is 5.896 inches. Quick note, I did want to use end caps on this tank, but I realized that these tanks have small enough radius that a bulkhead would do, and calculating the radius of the tank would evolve into a fourth order polynomial. For calculating the thickness of the concentric tank wall, I struggled. I tried to come up with different ways to do this, and this way probably doesn't work. I assumed the pressure was some multiples of the gauge pressure between the nitric acid and the diesel oil at ullage pressure, and I got like 84 psi. And then I added a bunch of safety factors and just multiples to get the thickness to be 0.0137 inches thick. This is questionable. The pressure in the tank operated at 2296.7 psi, so that also passes the requirements. Oh, this is out of order. So for the structure ratio, the unit weighs about 3,110.6 pounds dry and contains 12,044.26 pounds of propellant, so the ratio is 25.83%, which is greater than the quad unit. Since we know that this is a heavier unit, we can reasonably deduce that the thrust on this first stage is higher. It's 136.78 kilonewtons versus the 132 on the quad. This means also that the radius is greater than the 9.5 inches we were looking for at 10.37, so that also fails. Let's take a look at all of the units. The first part examines the structural side of unit design. Materials, propellants that exceed pressure limits, and determining the Better OTRAG unit itself. Since none of us want to examine every possible unit, all 792 of them, I'll be using WFNA diesel oil for the charts and plots. Oh, and I'm going to vary the unit height between 18 to 24 meters to look for trends and patterns in the structural side of things. An easy start is to change the pressurant tank material. Most of these tanks are going to operate at greater than 1,000 psi, which means they'll get really heavy really fast. For the Mar-Aging 250 units that we examined, the structure ratio is around 24% on average, which is really heavy. But if we were to change it to, T1000G, which is stronger and less dense, as you can see in this chart, it drops to about 13%, around half. You can see where we're going with this. Before we start looking at propellant tank material, I'd also like to take a look at the concentric tank units. Remember, in this case, it's a function of the height of the pressurant tank. So what you can guess is already intuitive by this chart. Shorter pressurant tanks means higher structure ratio than taller pressurant tanks. This should make sense because the shorter ones have less volume, which means more pressure to do the same job. Now let's move on to the material selection. We know that T1000G is the pressurant material, and likely the whole structural material, but let's prove it. For this, I've made two charts, one for the quad tanks and one for the concentric. Now, my study examines all three possible chamber pressures, but I'm only going to show you the 300 psi. And on the quad, now this looks like there's a lot, but we're only looking for the bottom one, and that is T1000G. And then for the concentric, it's T1000G. Well, we have our tank material, but do take a closer look at these charts. You'll notice that smaller, shorter units are favored, and that the quad unit is favored for both nitric acid and hydrogen peroxide. For the rest of these examples, I'm going to still use Mar-Aging 250 and T1000G for my tank materials because the structure ratio will be guaranteed to be above 6% and varies in a way that can show my points. When I was examining different units and propellants, I found myself focusing more on volume ratio than mixture ratio because there are mixture ratios that do overlap for some of these propellants, but volume ratios were definitely different because the propellants would have different densities. The most egregious example I found was WFNA methanol, because their volumetric ratio is about 1:1. So take a look at this 6-meter unit. With a chamber pressure of 300 psi, that pressurant tank is at 62,000. The lowest pressure units I found were hydrogen peroxide and RP1. And in fact, all of my peroxide units had pressurant tank pressures less than 3,000 psi. This plot shows the relationship between volume ratio and the structure ratio of 300 psi units. Blue are the concentrics and oranges are the quads. And aside from a few anomalies, the quads are all lower than concentric. Next, I examined the height percentage for concentric tanks. Now, since the way this works out is that all the tanks have the same pressures no matter which propellant, this became a very easy task. For 200 psi units, the pressurant height percentage had to be above 13%. For 250, it was 15.5, and for 300, it's 18. It doesn't matter. By selecting T1000G, a filament wound composite, this makes the concentric unit really hard to make compared to a quad. Also, quads are just lighter. So concentric tanks are eliminated. On to propulsion analysis. This section was mostly inconclusive. What I didn't take into account is the fact that different propellants have different performances, so the engine requirements would change accordingly. What I examined instead was the relationship between chamber pressure and engine radius for the different pressures for our notional OTRAGs. What I also included was varying heights and proportional payloads. The payload fairing mass would stay the same across all of them, of course, because it's the same size. Here is a plot of white fuming nitric acid diesel oil OTRAGs and their engine radii, including the 3 chamber pressures. The red line is 9.5 inches. 300 psi units barely make it under the limit, while 200 psi units are obviously struggling. This should make sense. Sure, the tanks will be thinner and the units will be slightly lighter, but you have to take into account the fact that chamber pressure is lower and the thrust coefficient is also a lot lower. In fact, I think it was so low we might have to worry about flow separation in the engine. I decided to figure out the maximum possible heights in the units to gauge trends in the propellants and the pressures. Table 4-5 in the paper lists all of them because I'm not going to list them here. From that, you can see that hydrogen peroxide units do very well for height, while WFNA units struggle. I suspect it's that hydrogen peroxide has higher mixture ratios, because peroxide's slightly less dense than nitric acid, and that the thrust coefficients are a teensy bit higher. Here are the propellants I eliminated: WFNA ethanol, WFNA ethanolamine, methanol, methyl acrylate, and triethyl citrate. I also got rid of dimethyl acetamide because I discovered it was actually really toxic. Rocket development is one of those industries where bad publicity won't help you. Let's fix something. My tank wall thickness calculations were built for metals, not filaments. What I did with the filaments was I just divided their tensile strength by 4 and used that as a knockdown factor to calculate wall thicknesses. This, moving forward, is obviously inadequate. Remember the fiberglass tanks? Take a look closer. You're going to see that they have both hoop and helical windings. The reason why should be obvious. But this means that you have to do more math to calculate the thicknesses of both the hoop and helical windings. So, how did I incorporate this into my structural analysis? I didn't! I found an online calculator instead to check my math against, and discovered that my knockdowns are actually pretty accurate. Instead, what I did was I used the actual tensile strength of the T1000G composite instead of just the filament, and I added another factor to increase propellant tank pressure. I called it the maximum expected operating pressure factor, that's what I called it, of 2.25. I also changed the ullage pressure to be 1.34 times the chamber pressure instead of 1.26, which is a lot closer to the original OTRAG design. So now the tank wall thickness is calculated basically the same way. The thickness is 2.25 times the Elch pressure plus the hydrostatic pressure times the radius over the new safety strength of the T1000G composite. Tank wall thicknesses on the 300 psi WFNA diesel oil unit go from 0.019 inches to 0.0235. This is a more reasonable number to work with. And I also set the end cap thicknesses to be the same as the cylindrical thickness, just for conservatism. I didn't do this for the pressurant tanks because, they're already operating at high enough pressure. For these orbital OTRAGs, to avoid spending hours and hours making spreadsheets, I decided to make the engine area ratios for the second and third stages to be 6 and 16. Now, this means that the units aren't optimized, but you'll still get to see patterns and trends on which propellants do better than others. And as always, I'll be using diesel oil for my examples. This figure shows the difference in payload capacities of the nitric acid and peroxide OTRAGs at 300 psi. You can clearly see that the peroxide OTRAGs have significantly better performance than the nitric acids. The peroxide one gets nearly 4.4 metric tons, while the WFNA gets barely 3.7. With chamber pressures, shown in this figure, there is negligible difference between 250 and 300 psi. Now, some of this is because there is no optimization, but the rest I suspect is due to different design factors and performances. We also have one other important figure to work with: the ratio of payload mass to gross liftoff weight. It has to be above 1%. For the non-optimized peroxide units, it's somewhere around 1.33%, while white fuming nitric acid struggles at 1.01%. Oh, and I did eliminate 250 psi units right after this because they just performed terribly. Now, keep this chart in mind as we move forward. None of the OTRAGs hit my expected target of 5.7 metric tons. The closest was hydrogen peroxide and DITA at 4.83 metric tons. Only 900 kilograms away. The worst performing was WFNA acetyltributyl citrate at 2.93. And because of this, it was eliminated right away. Take a good look at this chart or read the study before I keep going. Alright, so what you probably saw was that for the nitric acid units, only one fuel actually got above 4 metric tons to low Earth orbit, and for hydrogen peroxide, only one didn't get above 4 metric tons to low Earth orbit. And you'll see that the hydrocarbons naturally performed better, except RP1, which was eliminated. Now, before you get mad, this could be because of C-ProPep, or just the way the RP1 units worked out. I also eliminated hexane because I discovered it was a lot more toxic than I thought it was. Well, it seems like hydrogen peroxide and DITA is the better OTRAG propellant. Except that this is a multifaceted study. I'm not just going to slap the mission accomplished sign here and call it quits. We also have to consider the price of our propellants in the mystical figure of dollars per kilogram. Yes, I have criticized it before, but that's because people were using it inappropriately. Using it here, I can figure out which propellant gives me the most bang for my buck. And again, I must remind you that this method does not include the intricacies of actual launch vehicle design. So here's the dollars per kilogram for these, assuming that propellant is 0.5% the total launch price. Oh, and at this point I eliminated isopropanol because it performs basically the same as ethanol, but it's more expensive. What you see here is an interesting inversion. The highest performing propellant is $15,170 per kilogram, while a lower performing propellant, WFNA Jet A, is only at $6,742 per kilogram. I didn't just go with the most inexpensive propellant and call it a day. Remember, price isn't necessarily everything, especially with a crude study like this at this point. Instead, I picked the 3 most inexpensive propellants per oxidizer and went from there. For white fuming nitric acid, I picked turpentine, Jet A, and diesel oil. Yes, 1-pentanol is cheaper than diesel oil, but diesel oil is far more common. For hydrogen peroxide, I ended up picking turpentine, Jet A, and ethanol. This round has two improvements. The most obvious one is that I'm giving the second and third stages greater area ratios to work with and to optimize around. For the second stage, you go from 6 to 9, and for the third, 16 to 21 in increments of 0.2. Secondly, I'm allowing the unit radius to change from 11 inches to 15 inches in increments of ½ an inch. This will increase the propellant mass per unit and allow for wider engines. As an example, this is the 11-inch optimized 300 psi WFNA diesel oil OTRAG. It can carry 3.9 metric tons to LEO. This is a 15-inch radius WFNA diesel oil OTRAG, and it can carry 7.9 metric tons. This chart shows the disparity in performance based off of unit height. The lower one is the 11-inch radius, and the upper one is 15 inches. And this red line is the desired 5.7 metric tons. So what you can guess is that our optimal WFNA diesel oil OTRAG has a radius closer to 15 inches than 11. I'll optimize my units for radius and height next. The optimized WFNA diesel oil OTRAG unit is 23 meters tall and has a radius of 13.5 inches and has a dollars per kilogram of, oh my, 8,556. The WFNA turpentine unit is also 23 meters tall and has a radius of 13.5 inches, but this one is only $6,548 per kilogram. The WFNA Jet A unit is 24 meters tall and has a radius of 13 inches at $6,122 per kilogram. Now moving on to peroxide. The peroxide turpentine unit is 24 meters tall and has a radius of 12 inches at $7,195 per kilogram. The peroxide Jet A unit is 24 meters tall, has a radius of 12 inches, and is $6,955 per kilogram. And finally, the peroxide ethanol unit is 23 meters tall and has a radius of 12.5 inches with a dollars per kilogram of $6,692. What you see here is the same pattern as before. Nitric acid is cheaper while peroxide performs better. Better OTRAG is going to need one oxidizer though. I'm going to have to select it now. Time for a pros and cons list. The pros for nitric acid are that it's cheap, dense, and is better at hypergolic ignition with certain fluids like furanol, like in the original OTRAG, which means you could have a much more simple ignition system. And on the cons, it performs worse and it's more of an environmental hazard. The acid of acid rain is nitric. The WFNA part, the white fuming, are nitric oxides that are toxic. And the overall combustion products for nitric acid and whatever fuel are worse than peroxide. You want people to hear about your rocket company for doing cool things, not getting into yet another environmental lawsuit. For peroxide, it performs better. It's considered a green propellant because it's not as toxic as others, and it's also a monopropellant, which means we could use it for thrusters. On the downside, it's more expensive and does have some handling issues. Oh, and it's not as easily hypergolic as nitric acid would be, so it would require a separate ignition system, most likely. So what did I pick? Hydrogen peroxide. Yes, it is $600 per kilogram more to orbit than WFNA. But you also have to consider how much of that $600 per kilogram would be lost in environmental lawsuits and in regulations. Imagine a nitric acid OTRAG failing early on into flight and smearing nitric acid all over the place. WFNA is out, and so is turpentine. It's too expensive, and I discovered that the pine trees needed to make the resin that turpentine is made from don't grow in equatorial regions where our troubled democracy is located. So this leaves Jet A and ethanol. I've made two more improvements before the final decision. The first one is one I brought up way back at the beginning of the study, which is related to tank radius. Up until now, the tank radius has been the unit radius, so 5.5 inches. But I've been ignoring the tank wall thickness that I keep getting. So if I have a tank wall that's 0.02 inches thick, that means my unit radius is actually 5.52 inches. Well, I fixed that. Now I've optimized this around the internal tank radius being whatever it needs to be so that the total radius is whatever I set it to be. Now this will decrease propellant volume in the tanks, but we can compensate for that. The second optimization I did was allowing the first stage engines to have an increased area ratio. If you look at any old BDB study with a 300 psi engine for the first stage, you'll discover that the area ratio is 5, not 4. So I allowed this to be optimized in increments of 0.1 up to 4.6, which is what both of them got. I also allowed for the area ratio of the third stage to go up to 21.1 and 21.2. I swear I could hear dogs barking or children screaming. Oh well. Our Jet A OTRAG can toss 5,853 kilograms to low Earth orbit, an improvement of 111 kilograms. The price also dropped from $6,955 per kilogram to $6,766 based on this improved performance. I discovered that every 0.1 increment to the area ratio of the first stage increased the overall delta V by about 30 meters a second at least, whereas on second and third stages the same increment wouldn't do as much, by about a quarter. With ethanol, the payload increased by 93 kilograms, up to 5,797 kilograms, and the price dropped, of course it did, to $6,531 per kilogram. In terms of the ratio of payload mass to gross liftoff weight, the Jet A OTRAG sits at about 1.47%, while ethanol is at 1.34%. This makes sense since ethanol performs worse than Jet A. We are again at an impasse. What propellant do I pick? The one that performs better but is more expensive, or the one that's cheap but performs a bit less? To look at this, I examined an entire family of OTRAG vehicles, not just our 64-unit baseline, but a lot more, to see if there's any wild differences in performance between Jet A and ethanol. Ethanol only really performed about 1% less for payload than Jet A, but at $200 per kilogram less. What did I pick? Ethanol. In this case, price beats performance. Also, there was some novelty to it. How many alcohol-based rockets do you see flying today? So I figured, why not? Another is availability. Jet A is used exclusively in commercial aircraft, so the price of it and availability of it would be dependent on the aircraft and air industries of this country. Also any sanctions. Whereas ethanol can be produced locally and used in other commercial ways. Fun fact, you can make ethanol at home with the proper licensing. Now, if it turns out that my ethanol price is way too low for what it actually is, or my pricing scheme just didn't work out properly, I would switch back to Jet A for the fuel. Jet A has also been proposed for other low-cost launch vehicles, and the combination of hydrogen peroxide and Jet A was actually the choice for the Beal BA2. So who guessed it? Here's our Better OTRAG. Each unit will comprise of 2 oxidizer tanks containing 90% hydrogen peroxide, 2 fuel tanks containing ethanol, and 2 pressure tanks containing compressed nitrogen gas. The propellant tanks will operate at 402 psi, while the pressure tanks will operate at 2084. These tanks, all of them, will be made of Toray T1000G epoxy composite and have an HDPE liner. The unit is 23 meters tall and has a radius of 31.75 centimeters. Each unit contains 6,248.7 kilograms of propellant and weighs 421.9 kilograms dry. Every 3 meters is a collar wrapped around the unit for structural purposes and to act as attachment points for wiring, plumbing, sensors, and other equipment for the unit. A third stage unit's engine operates with 39.25 kilonewtons of thrust and has a specific impulse of 285.55 seconds. The second stage has 89.09 kilonewtons thrust and operates at 269.88 seconds ISP. The first stage is 132.86 kilonewtons of thrust with an average specific impulse of 241.08 seconds. I was going to attempt to look at engine cooling methods, but I ran out of time, and I did try this earlier with the first attempt at this study using Hutzel and Hang's example, and I got the exit ablator thickness to be 0.47 inches while the throat was 1.1 inches thick. This would change the area ratio from 20 to 10 and lower performance accordingly, which is not good. As for steering, I also didn't have enough time to examine this, but I did read that throttling the engines was a great way of steering. It's more simple than liquid injection thrust vector control, so we'll just assume that. Now, for single unit upper stages, steering will be done by cold gas thrusters on the payload attach fitting. That seems reasonable. Construction of the Better OTRAG begins by mass production of propellant tanks and engines, which are assembled and then stored at pressure to prevent implosion. For a full launch vehicle, they are assembled horizontally, rolled out to the pad, and then erected there. Fueling of the units is done on the pad at the base of the tanks using a removable pallet system. The nitrogen pressure tanks are done something similar or in the horizontal integration facility, whichever one is more safe and practical. And at liftoff, Better OTRAG weighs at most 435 metric tons. Engine ignition is done by running hydrogen peroxide over a catalyst which decomposes it into hot hydrogen, oxygen, and steam, which will then ignite, hopefully on contact with ethanol. If that doesn't work, you'd use a separate ignition system. Ignition of the second and third stage engines, at least during the initial ascent, are done using hot staging, since this simplifies things. The second stage engines will ignite before the first stage engines are shut down. This means that the propellants are already settled at the bottom of the tanks, and they can be put into the engine simply. For upper stages, for later burns, we'll use a cold gas thruster system to provide ullage to settle the propellants at the base of the tanks for a second ignition. I smell a problem. OTRAG has two upper stage problems. The first one is that it's possible that the upper stage is not capable of engine restart. This is unlikely, but considering no one's ever really built an OTRAG style stage, it is possible. But the second, thermal, is far more pressing. Space is both hot and cold. It's possible on long duration missions that the propellants will either freeze or boil in the tanks before the next engine burn. Now, on conventional launch vehicles, this is quite an easy fix. Insulation. On OTRAG, I do have a solution, and that's modular kick stages. These will obviously enhance OTRAG's performance to low Earth orbit, but more importantly allow heavier payloads to be sent to higher energy orbits. I haven't shown you any performance figures yet, but OTRAG's performance beyond low Earth orbit is abysmal. Now, this wasn't as intensely studied as the rest of this because the primary focus was Better OTRAG, not better kick stages. So keep that in mind. But I did optimize this around a 2-meter high unit, roughly, with an engine that has a 300 psi chamber pressure and an area ratio of 100. They're clustered, that's a shock, in 1, 3, 4, 6, and 8 bundles. Which means we have propellant varying from 636 kilograms on the smallest one up to 5,090 kilograms on the largest, with the dry mass assumed to be about 19% of that. I also included a Star 37 FM and Star 48B upper stages, as well as room for a notional liquid space tug or something of that sort. Besides augmenting the baseline high energy orbit capacity of Better OTRAG, these kick stages could also be used as space tugs. Space tugs enhance our mission capabilities for long duration missions, or for rideshare missions that have to go to multiple orbits. You can do that now. Let's take a look at what I've made. Better OTRAG has a 3 to 4 digit nomenclature. X, the first number, is the square root of the number of units in the vehicle. So 3, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. You'll notice I'm missing 4 and 6 because the 16 and 36 unit OTRAGs could not be optimized effectively. So I just gave up on that. Y refers to the number of stages for the vehicle. So it's 3, 4, and 5. For 3 stages, 4 stages, and 5 stages. Now these are stages made of the basic OTRAG unit. I only looked at 3 or 4 stage OTRAGs for this, but 5 is possible. And Z refers to the upper stages you might have on top of this. So none, the 1 through 8X kick stage, the star 37FM or the star 48B, plus the notional liquid tug that I just left room for. This makes our baseline 64 unit Better OTRAG become an OTRAG 830. Now you can explore all the different combinations of OTRAGs you can make in the spreadsheet I provided, but I've got to warn you about this. One problem is that I didn't give you limits to what you could put on different vehicles. So for example, you could put an 8X modular kick stage on top of a 330, which you obviously can't do. And the second problem is that I did not take into account thrust to rate ratio limitations, so there are some combinations that would not work because they just wouldn't move. Keep that in mind. So let's take a look at what a few Better OTRAGs can do. Since I don't have an orbital launch calculator and I couldn't build one in time, I just decided to use delta V to examine performance. 9.5 kilometers a second is the delta V to go to low Earth orbit, and 12 kilometers a second is geostationary transfer orbit. And I'll be ignoring that 70% capacity set for the low Earth orbit version, because that's just, we don't need that right now. I was also to examine different launch sites like Malindi, Alcantara, and Biak Island, but that's not really related to this at this point. This chart shows the capacity of the OTRAG 830 at different delta V's from low Earth orbit to geostationary transfer. 5.8 metric tons all the way down to 812 kilograms. Now remember, your average geostationary satellite starts at about 4 to 5.5 metric tons. Just show us the big ones. Fine, let's take a look at our basic 3-stage OTRAGs, which vary from 9 to 256 units. No, you can't build one any bigger than 256 units. That one is 10.2 meters across, which is wider than the Saturn V first stage. Oh, and I did my best to optimize the bigger ones. And I'm not going to include the 70% capacity figure because I'm not going to do that. OTRAG 330, 469 kilograms to LEO. The 530, 2.15 metric tons. 730, 4.339 metric tons. And obviously our basic 830, it goes down to 5770 kilograms. Some of the rounding I did fix that. The 930, 7464 kilograms. The 1030, 8723 kilograms. 1130, 10,384 kilograms. The 1230, 12,673 kilograms. 1330, 15,503 kilograms. 1430, 17,699 kilograms. The 1530, 19,869 kilograms. And our 1630 is 23,171 kilograms. In terms of launch capacity, Better OTRAG can eat the entire launch market, from Electron to Falcon 9. When looking at geostationary capacity, I'm only going to look at the 256 unit because it's the biggest. Your baseline 1630 OTRAG can toss 3,333 kilograms to geostationary transfer orbit, which is close, but not enough for the current launch market. Now, if we were to turn this into a 1640, this capacity goes up to 7.3 metric tons. Just a scooch above the current largest geostationary satellite launched that we know of. How did this happen? Easy. I took the 16-unit third stage and turned it into a 4-unit fourth stage and 12-unit third stage. If we were to add in the 8X upper stage, this bumps up the payload capacity GTO to 8.3 metric tons, or 3.4 directly injected into geostationary orbit. You can see how these kick stages enhance the performance. So what about pricing? This is the final change to the analysis. I was going to optimize the payload fairing to fit, kick stages and reasonable sized payloads, but I just ran out of time. What I did was I changed the worst case propellant pricing from 0.5% to 0.666666666% because I realized that OTRAG could have a 30% price reduction through mass production and the way it's built. Am I cheating? Yeah, a little. But you've got to remember, this number is kind of come out of the air and it kind of works for high-performance pump-fed rockets in the first place. So this chart shows the payload capacity of all three-stage OTRAGs based on their price in terms of dollars per kilogram. The upper one is the conservative, the lower one is the optimistic, which is a quarter of that. So we're talking about $5,000 to $1,250 per kilogram. The rest of these dots, the blue ones, are existing launch vehicles. And you can see the only one that might give OTRAG a run for its money is a first stage reused Falcon 9. How about that? Ha! So even you admit that Big Dumb Booster can't beat Falcon 9. Don't go there. Wait, how did you get here? Guards.
We have a problem.
What? I'm busy. Oh, you're embarrassing me in front of the gringo missile guy. What?
These people want a revolution.
Who? Hey? You want a revolution?
Viva la revolución.
Viva. Please go on.
Before we talk about the reality of OTRAG, let's butter ourselves up with the good things. Modularity. As you can see, you can make a launch vehicle capable of eating the entire launch market. And with the same one, you can change how the stages are ordered to reach higher orbits with different payloads. The payload fairing is huge. You can put in a very low density payload in there with great ease. And for rideshare missions, this is really easy because you just stack the payloads next to each other. For pricing, the big figure is how cheaply and quickly you can mass produce propulsion units. Mass production has allowed for the creation and selling of relatively inexpensive electronic products, and it's reasonable to assume that there could be some components that apply to launch vehicles. Also, mass production means you can have a quick and easy development cycle, as evidenced by the original OTRAG. That's about it. As I've talked about before, there are two questions we have to ask ourselves about this. Is this technically possible? And is it practical? Technically, possibly. My study is too rudimentary to say absolutely yes or absolutely not. My structural analysis was too simple and ignored things like bending moments, twisting, and other forces that would impact the structure of a unit. I ignored aerodynamics. My propulsion analysis was very bare bones and incredibly simple. My pricing scheme was, well, way too simple to be practical. I focused entirely on propellant pricing. And I ignored things like, well, manufacturing costs and the price of materials. I don't know what T1000G costs. All I know is I hope it's not too much more than fiberglass. The real question then becomes, is OTRAG as a design concept practical? No. Sorry, that thing's not practical. Take a look at it, and you already have your first question. How do you build this thing? Most launch vehicles are either integrated horizontally or vertically. And those are really easy to do. OTRAG? Neither seem too easy, but we'll go with horizontal. Even then, OTRAG is a clustered system. I can see how individual units could be attached, but I don't really know how big stages could be built. I've spent about a year thinking about this, and all I can think of is how the top of the unit and the bottom of the units are attached to each other in each stage. The bottoms would be attached to a gridded table structure that would hold the units. They'd be attached on the top of this, and then the engines would put on the bottom. and each stage would have its own table, and the tables would nest on each other so that the second and third stages don't roll out the back. But as for the middles, I don't know. I don't want them to splay outward during a launch, if you catch my drift. This wasn't covered in any of the discussions about OTRAG I can find. I can't find any publicly available technical papers that discuss this or how OTRAG was assembled in any way, aside from the single units. I don't know how to do this, but I'm going to assume it's very complicated. Also for staging, there is another issue, and it's not heating. Just so we can get this cleared up, if you cut the OTRAG in half when the first stage is firing, you're going to notice that the inner stages aren't, and there's going to be a heat plume from the engines around them, and it's going to try to climb up there and probably climb up into the tanks. This can be fixed by putting a heat shield over the base that's, for each stage, and something that can cover the engines and all the attachments there to keep them from being damaged by this. You don't want the heat plume to climb up into the tanks because it might damage the composites. You don't want it getting into the payload fairing. You don't want it to also mess with the propellants either. And I just realized the plume would also climb up the side of the outside. I just thought of this. We're just going to keep going. The one I'm most concerned with is staging. The second stage is nested in the first one and is going to fly out in flight. The concern I have is, what is the exhaust plume of the second stage going to do to the tankage in here as it's flying out? Also, any start-stop transients from these engines. To put it simply, I don't know if the tanks will vibrate in a way that could damage themselves or other ones or bonk into the engines. Dynamics! Still on the first stage. The payload fairing, as you can see, is part of the first stage structurally. The benefit of this, of course, is it's enormous. The downside is this means that the first stage has to do a lot of work. It's got to get OTRAG up and out of the denser part of the atmosphere fast before staging, because I don't want the payload to be shredded by aerodynamic forces the second this thing opens up. This puts a lot on the fairing. Now, there might also be other problems with the fairing as a concept in the assembly process, but I didn't focus on that. Instead, we're back to ground support. What kind of launch pad would we need for Better OTRAG, the whole vehicle? Unlike conventional modular launch systems, OTRAG's width varies greatly, from about 75 inches all the way to wider than the Saturn V at 30 feet. What kind of launch pad could you build that could support both of these realistically? I don't really know. Even on the pad, there are going to be issues. Uneven heating. OTRAG is going to be subject to sunlight on one spot more than the next. This is going to cause uneven heating. On conventional launch vehicles, this is fine because, well, your propellants are all mostly in one tank, so it's kind of easy to work around. But with OTRAG, it's one unit, or a handful of units, they're getting hotter than the rest. Now remember, PV equals nRT, so these propellants are going to get higher pressure than the ones on the other side. Put simply, you're going to have a lot of propellant management and monitoring systems on board. Fueling is a challenge too, because how would you know if a unit is full? Or if there's a leak? Or what if there's a broken part? And this is all I can think of off the top of my head. An easy way to imagine these problems is through money. OTRAG is going to save a lot of money through ultramodularity and mass production, especially with low-cost pressure feds. That's a given. However, some of that savings is going to be lost in development. Sure, OTRAG is simple, but you still have a lot of components to work with per vehicle. Engines have to operate within tight tolerances of thrust and impulse. Valves have to turn at the right time in the right place in an intense environment, and you can kind of get the picture here. Yes, we do have mass-produced parts, somewhat like the ones we'll see in Better OTRAG running around today. Originally, OTRAG used windshield wiper motors to turn the valves, but that was eventually changed. What I'm getting at here is, yes, we can mass produce parts that don't fail very often, but those parts don't have to operate in the same intense environment that rockets do. You're also going to lose money on assembly and ground support. OTRAG is hard to build. Each unit is going to have to be inspected, checked out at both the assembly building and on the pad. Think of all the fueling ports, the wiring, the plumbing, the valves, that all have to be looked at and made sure they're all in the right place for every vehicle. Some of this can be solved through iteration and the development process, but there are fundamental limits to what you could realistically do. I see ground support and assembly as the biggest bottlenecks to OTRAG's effectiveness as a launch vehicle. If you read Rupa's analysis, that's the one that points out that OTRAG units were too heavy and the engines couldn't reach the performance that Kaiser was saying. He suggests that OTRAG would probably be more expensive than equivalent commercial launch vehicles. At the worst case, $25,000 per kilogram. That's a low flight rate, and $5,000 per kilogram at a high one in 1980. Granted, I did solve some of the problems he outlined, but plenty still stand. This is a hard design to make work. OTRAG was designed around mass production of simple propulsion units and modularity, and not much else. To combat this, I examined alternative launcher designs based off old big dumb boosters. This should show OTRAG's strengths and weaknesses. I examined 5 possible alternatives: a 3-stage classic big dumb booster, a 2-stager, a modular vehicle like Pertron or Scorpius, another modular system like the multi-purpose nano missile system, and Al-Abid. Okay, Al-Abid was a joke and the 2-stager just didn't work. Not to get bogged down in the details, but I did follow a similar design style for this vehicle as I did with OTRAG. But this time, the top tanks are 1.5 times the pressure of the chamber, while the bottom tanks are 1.26. Tanks themselves are 62%, 52%, and 42% the total weight of the first, second, and third stages. This is in line with more conventional launch vehicles and old BDB studies. Upper stages have different performance requirements and other accoutrements that first stages don't, and they'll scale differently. For the modular vehicles, both the first and second stages, since they're the same unit, will use the 62% figure. Also, on some of the modular vehicles, the first and second stages will have the same engines. The rest is optimized for 5.7 metric tons. I did examine using 300, 250, 200, 150 psi chamber pressures on upper stages and optimized around performance and mass, which should make sense. There's other things I did that I just don't want to include here. This part's going to feel a bit crude and rushed. Don't worry, the study does go into more of the design analysis that I did, focusing on things like, for the modular systems, the ratio of the third stage mass to the second stage mass, chamber pressures, and how many boosters are in the baseline vehicle. Go take a look at that. I designed this around propellant mass and mass ratios instead of the size of a unit because you can guess. Let's take a look at them. We're going to start with the OTRAG 830 to get a picture of what's going on. Stage 1 weighs 434,784 kilograms at liftoff and has 48 engines burning at 132.8 kilonewtons each, with an average specific impulse of 241.08 seconds. Stage 2 weighs 112,989 kilograms at start and burns 12 engines with 92.35 kilonewtons of thrust and 269.399 seconds specific impulse. Stage 3 weighs 32,939 kilograms at start, with 4 engines burning at 40.4 kilonewtons of thrust and 285.6 seconds specific impulse. To LEO, it can throw about 5.77 metric tons at $4,891 per kilogram, conservatively, and $1,223 optimistically. To GTO, it's about 803 kilograms. The classic BDB weighs 391,337 kilograms at liftoff with a single 300 psi engine with 5.18 meganewtons thrust and a specific impulse of 237.56 seconds. Stage 2 starts with 116,497 kilograms with a 250 psi 1.37 meganewton thrust engine that has a specific impulse of 280.9 seconds. Stage 3 starts at 26,052 kilograms with a 200 psi engine that has 204.4 kilonewtons of thrust and a specific impulse of 302.9 seconds. This can throw 5.7 metric tons to LEO at $4,475 per kilogram conservatively and $1,119 optimistically. The GTO performance is 879.7 kilograms. Percheron Scorpius was optimized around a 250 psi engine unit and a 200 psi third stage with 1/4 of the propellant mass as the basic unit. 3 units are on the first stage. The gross liftoff weight is 377,633 kilograms, and each engine has 1.73 meganewtons of thrust and a specific impulse of 237.3 seconds. Stage 2 starts at 115,092 kilograms with a single 1.73 meganewton engine with a specific impulse of 251.4 seconds. Stage 3 starts at 27,578.4 kilograms and has a thrust of 162.7 kilonewtons and a specific impulse of 298 seconds. This can toss 5.7 metric tons to LEO for $4,404 per kilogram conservatively and $1,101 optimistically. GTO payload is 1,352.9 kilograms. M&M's was based off of one design you usually see in all solid launchers. The first and second stages use the same tanks, but slightly different engines and are stacked on each other. Engines here are 300 psi and 150 psi. The gross liftoff weight is 365,963.9 kilograms. The first stage engines have a thrust of 1.794 meganewtons. Stage 2 starts at 105,359 kilograms and has a thrust of 1.24 meganewtons, with a specific impulse of 281.2 seconds. Stage 3 starts at 18,491.1 kilograms with a thrust of 109.3 kilonewtons of thrust and a specific impulse of 302.2 seconds. Conservatively, this can carry the payload at $4,222 per kilogram or $1,055 per kilogram optimistically. The GTO payload is 1,252.2 kilograms. Al-Abid was a joke based off of the only launch vehicle produced in Iraq before the Gulf War. The study lists what it can do. Of these alternatives, what did I pick? Not Al-Abid. M&M's was eliminated for price and structural reasons. It's too expensive, and that thing's gonna wiggle funny. I just know it. This leaves the classic BDB and a Percheron-style modular vehicle. Now, the classic BDB is very cool and all, but it's not modular. And the Percheron vehicle can carry more to low Earth orbit and to geostationary transfer orbit. It's modular, and price-wise it does actually beat Better OTRAG, which, that's a given. Now, if you're aiming for something more like first stage reuse, then you're gonna go with the classic. That's a lot easier to do. Percheron still allows mass production of propulsion units, not at the same scale as OTRAG, but these can be specialized for their purposes, instead of having to be both a first and last stage. Using a common diameter and the same propellants on the stages will also reduce costs. Conventional modularity does leave payload gaps, as I call it, where a payload might be too big for one vehicle, but kinda small for the next one up. But you have rideshare opportunities. The bigger one will allow better performance range, in case something goes wrong. And no one worries about this in real life. We've seen this already. And this means you can also optimize for a specific market instead of trying to eat the entire thing. Plus, with these designs, you can actually examine alternate propellants that aren't as constrained as OTRAG. So you talk about propane, ethane, even using liquid oxygen and optimizing around there, which could further improve your performance. And with a propellant like LOX propane, you could experiment with vapor pressurization so you don't need big heavy pressurant tanks. But we'll leave that for another time. Let's take a look at Better OTRAG. It can come in 5 different versions: a 2-stage vehicle, a 2-booster vehicle, 3 boosters, 4 boosters, and 6 boosters. I thought about adding 5 in there to match the Eagle family, but that's too unconventional. Oh, and you'll notice that these are physically larger than their pump-fed counterparts. It's called Big Dumb Booster for a reason, folks. The 0-booster 2-stage vehicle can throw 1,164 kilograms to LEO, so it's something like Firefly Alpha in terms of payload capacity, but can't toss anything to GTO. The two-booster vehicle, which might have too low of a delta V on the first stage, can throw 4,365.9 kilograms to LEO and 875 kilograms to GTO. The three-booster is what we've already seen, so I'm not going to repeat it. The four-booster version can throw 6,753.6 kilograms to LEO and 1,779.7 kilograms to GTO. And six boosters can do 8,759.1 kilograms to LEO and 2,517 kilograms to GTO. It's possible that you could make this into a four-stage vehicle and increase capacity. On this chart, you can see that Better OTRAG exists in a bit of a capacity gap. It's probably too big to carry small lift payloads, and it's too small to carry geostationary payloads. If I was asked to develop a low-cost launcher that was built like Pertron or Scorpius, I would focus it on either the small lift market or something larger. I would also examine putting alternative upper stages to reach higher energy orbits on the vehicle. So this would turn into something that's a hybrid of Pertron, Scorpius, and Conestoga, I guess.
You stupid American! You told me that this would make a great missile design! Where is the missile?
I can fix that. Well, there you have it. I designed a Better OTRAG. I parametric studied a Better OTRAG. Doesn't roll off the tongue as well, sorry. While the OTRAG design concept is possible, it is extremely unlikely to ever be a practical commercial launch vehicle, especially in the face of a more conventional modular launch system. OTRAG is an enigma. On the technical side, it's just an oddity among other designs. The rocket is a distinctive and creative solution to low-cost launch. Sure, it doesn't actually work, but just look at it. And then there's the story. It's more of a thriller than anything else. West Germans building a rocket in the middle of Africa. France and the Soviet Union collaborating to try to stop them. Rebel groups poised to take the site. And flamboyant dictators. It's something out of a movie. A Better OTRAG is Percheron. Maybe Gary Hudson was onto something. I couldn't have done this myself. Better OTRAG would not be possible without these fine people. Astro Freaky, our dictator. He's a Spanish-speaking space YouTube channel that talks about space and space flight. In Spanish! Check him out. Or else. Dan Moser, President and CTO of Composite X Inc., which specializes in filament-wound composite structures and other aspects of rocketry. His notable work includes being the former Director of Engineering at Beale Aerospace, design work for Scorpius, Quick Reach, and Truex Engineering launch vehicles, among other very cool projects. Tristan Hagerman, reaction mass enthusiast. Brenton Cassie, not a mercenary. James Clem, founder, Bantam Space LLC. Tome Fernandez, propulsion madman and Gamma 8 enthusiast. Scott Ullman, oh, this has to be withheld. Jack Miller, Aperture Lunar Sample Return Project, chemical propulsion test engineer. Mastered fluorine-based oxidizers and did so well he helped work himself out of a job. He does not know what happened to those astronauts. I think this is a joke. Hungry Tacos, CGI creator and propellant taster. Say, I wonder what big project I'm going to do next time. Is there any about Rob Long Gun? No! OTRAG! Well, got that out of my system.